Recording. So today we are going to go through the mutability and imperative control flow section. Let me paste the link in the chat. Feel free to ask questions if you have. I have pushed the notes for today's session to the GitHub Twitch repo as well. And we will try the examples as we go along. So this comes under the language section in the menu bar, and some of the examples we've already seen, so it will be like a good revision as well, but we'll look at more examples using UTOP. So the important thing with OCaml is it is practical, so right, you can do imperative style programming as well, although the preference is to use functional style. Now in the case of the let binding, it is immutable, right? The value is immutable, so it is impossible to mutate. Okay, let me open UTOP here. And yeah, we'll quickly go through revise the references section. So we already seen how to define references. So I can say let D is equal to reference 0, which means the contents in D, the value is 0, right? Now if I ask for the value of D, it says the D's contents is 0. And then I can imperatively set it to 1, okay, and again I can check D and it says the contents is 1. If I want to get just the value, I would just say I just dereference it like this using the exclamation symbol, and I get the value of 1, right? So the assignment operator equal to is used to update the mutable value inside D from 0 to 1, and the dereference operator reads the contents of the mutable value inside D. So that is the usage example here. So let's look at the operator definitions here. So if I do, let me just clear this UTOP output so I can check what is the assignment operator. It's just a function. It takes the reference to be updated, right, and the value that it replaces, okay. So the update takes place as a side effect and the value is returned. In the case of a dereference operator, let's see what that definition is. It's also a function. It takes a reference and returns its contents. That's pretty straightforward here. Right. The next example of mutability is record fields. We've already seen this before. So any field in a record can be tagged using the mutable keyword. So let's take an example here. Let's define a book record. So this can have a series number, can have a volume, can have a title string. We'll see an example next. Name of the author, and the stock here refers to the inventory stock, okay, the quantity. That alone we are making it as mutable, and let's close this. That's a book, okay. Now suppose we have a database entry for this book. How will that look like? So let's define volume 7. So I'm going to define this as the series belong to some motherboard diaries and the volume number is 7. Title is system collapse, right? And the author name is Martha Wells, and say the stock is 0, as in there is no stock of the books of this book available. Okay, so now if I get new stock, right, what happens here is I can say volume 7 dot stock, incrementing the inventory stock to 10 plus 10, and then now if I ask for the values, now it says the stock here is 10, right? The inventory stock is 10. So very simple example of using mutable record fields. Now there is no special syntax to dereference a mutable record field. Okay, so you just have to ask for this entire entry here, which is what is given here. Now we have already seen the definition of reference. Let's show it again. So we know that the contents field is actually defined as mutable, right? Now these references, we can define functions that operate on them, right? So examples like create, assign and deref using the mutable record field update syntax. So let's try this. So we are defining create. So I'm setting the contents to v, whatever I'm passing as an argument. Then I'm assigning the value here. So f dot contents will be v. Then to dereference it, I just get the value in the contents, right? Let's go through an example here. I'm saying f is create 0, and then I want to dereference the value is 0, right? Now I'm assigning 2 to it, which means assigning 2 to the contents, right? And I dereference that, and now get 2. Okay, so the create does the same as the reference function provided by the standard library, and assign is the same, so function is same as the equal to operator. Dereference is same as the exclamation bang operator. The next example is arrays. In OCaml, an array is mutable. It's fixed size data structure, so you can use it to store elements of the same type. They are indexed by integers. They provide constant time access compared to the linked list that we saw earlier, right? Also allows to update the elements. Let's look at example here. You can use Control L to clear the top screen. Let's define G as 2, 3, 4, 5, 6, 7, 8. Okay. Now I'm asking for G of 0, which is 2. I'm changing G of 0 to 9. Okay. And now I'm going to ask for G of 0. It is basically changed to 9. So you see the update in place for the array. Okay. Moving along, we'll now look at bytes. So bytes type in OCaml, it represents a fixed length mutable byte sequence. So each byte element has 8 bits. Okay. And byte values are mutable character sequences. So like arrays byte sequence support indexed access. So let's look at this example here. So we have let h is equal to bytes of string cd, f, g, h, I, j, k, l, m, n, o, WRSTUVWXYZ, right? Now I can do bytes dot get from H 10th, that's K, right? I can do bytes dot set H10, set it to underscore, and if I ask for H, now I see that K has been replaced by underscore. So byte sequences can be created from string values using the function bytes dot of toString, and as you have seen, the individual elements in the sequence can be updated or read by their index using bytes dot set and bytes dot get. Remember that byte types uses a much more compact memory representation than the character array, something we have to remember. So let's look at example getChar function. So we want to read a key from the user when it is pressed, and it returns the corresponding character. So there are two examples given here, two functions from the Unix module, and so we're using tc get attribute for standard input and we flush it, and similarly tc set attribute to change the terminal attributes. Okay, so the steps that are going to be followed here, same logic. So we'll see the slight difference here. We want to read and record the terminal attributes, set the terminal attributes, wait until the key is pressed, read the character, restore the initial terminal attributes and return the read character. Okay, and we're going to use the input char underscore char function from the OCaml standard library. So we will have to do require Unix here. So let's first use top find so we can find any libraries installed on the system. Then I'm going to say require Unix. Okay, let's define the first implementation of getChar. Let open Unix in. I'm going to get the attributes in, let echo term io dot c canon term io dot c echo in, right? We set the attributes term io canon false, then we have term io dot c echo to false, don't want to echo it, tc set attribute stdin, we flush term io, then we say let c is input character in channel of stdin, in term io, we restore the previously saved values, right? C underscore echo, then we set the attributes back, flush term io, and then we finally return the character. I hope I've not made any mistakes. That's good. So now if we can call this function getChar, right, it will prompt for a character. Say I'm typing A, it doesn't echo it, but it just returns the result. Okay, this is the second implementation. here the record returned by the call to TC getter is not modified. So we make a new copy with the term IO with ICANN false, right? So it only differs from the term IO value on the fields, and then we restore the terminal attributes to the initial state. So let's try this example here. So we have getChar is equal to, let open Unix in term IO attribute stdin in, we call attribute stdin flush, right? Here we are just instead calling term IO with CICANN equal to false and echo is false, and then we say let C is input char in channel of stdin in tc set attribute stdin tcsa flush term IO, and we return the character. Okay. Hope I've not made any typos in here. TCSA flush, that looks good. C underscore ICANN false, input char in channel of description stdin, and let's try to call the same getChar. Now let's say I do B and it returns character B, so that looks fine. Now let's quickly go through some of the imperative control flow expressions available. So we've already seen the let usage, the let in construct. The names can be bound in let. In this example, we're not binding it to anything. So I can do print string, this is in print end line really disco, right? So it returns unit. So side effects can take place in the sequence. Right? Now remember that the single semicolon operator is known as a sequence operator. So you already seen this in the previous example here. Right? We see all the semicolon usage here, right? So although it is an operator, right, it's actually a construct of the language. It allows adding a semicolon at the end of a sequence expression. So let's look at this next example here. So I can do let, not binding it to anything. It's going to say print inline hello semicolon. It's going to continue in this sequence, right, world, and then return 42. So even though it prints hello world, what is actually returned last is 42, right? This, the semicolon operator is used to separate these expressions. The other example here again is if I do unit 42 and semicolon like this, it returns 42. The semicolon after 42 is actually ignored. Now consider an example where we want to increment a variable r. Okay, we want to increment a variable r, and the returned value we want to multiply it by 2 and assign that new value back to r. Okay, so if you try something like this, let fr is equal to r, increment to r 2 times, this will basically throw an error. So if you want to like scope down the expressions, you need to use the begin and parenthesis constructs. So we have to use fr is equal to r equal to begin increment r multiply the new r with 2 and the result you reassign it to r. Okay, that will work. That's the actual implementation for what we want to do. So the begin, end and parentheses are just the same. So right, it's just unit. We have seen if then else examples. So let's try those. So 6 times if foo equal to bar. Note that we are using only a single equal to here. Then 5 else 5 plus 2. Right. So 7 into 6 will return 42. The conditional expression return type can be unit if both the branches are also returning unit. So if I say 0 equal to 1, then print end line foo, else also has a print end line. Right? It will print bar. You can also rewrite the previous expression like this. Right? Print end line. If 0 equal to 1, then foo else bar. So it returns bar, and that goes as an argument to print end line. That is also possible. The unit value can serve as a no op only when one branch has something to execute. Right? So you can do if 0 is equal to 1, then print end line foo, else just the unit. Okay. Now in OCaml you can write if then expressions without else. So I can just say if 0 equal to 1, then print end line, it just returns unit. Right. So in parsing, conditional expression groups more than sequencing. So let's try this example. If true, then print end line A, else print end line B, and then there is print end line C. So it prints AC because it's true. It prints A. It doesn't go to the else. It goes to the next command after the sequence operator. It prints C. Okay. Now, if you want to have 2 prints in a conditional expression, you have to use begin end. So we clear the output here. So if true, then we say print end line A, else begin print end line B semicolon, and then we say print end line C, the end. Of course it prints A, right? Now if you don't use the actual grouping, you will get an error. Like if you write something like if true, then print end line A, and then say print end line C, and call just else print end line B, so throw syntax error. Right? So you have to make sure you group the commands correctly. We have seen for loops. A for loop is an expression of type unit. So we can do for I is equal to 0 to 5, do printf dot printf percentage I slash n I done to print 0, 1, 2, 3, 4, 5. I is the loop counter. It is incremented after every iteration. 0 is the first value of I and pi is the last value of I. Okay. The next example using arrays. Let's try this. Let j is equal to 2, 3, 4, 5, 6, 7, 8. I can say for I is equal to array dot length of j minus 1 down to 0, do 0, done. Down to is in decreasing on every iteration of the loop. Okay, and it returns unit. The same thing you can do with the iterate. So let's do the for loops for modifying arrays. So I can say let sum is equal to reference 0 in. I can do for I is equal to 0 to array dot length j minus 1 do sum equal to, take the sum value plus j ith value call done, and then you return sum. Right, so that's 35. Now you can also use the iterator function given here. The same thing we can do sum is equal to reference 0 in array dot iter. Take a function sum is equal to sum plus I. J, and then finally return sum. Return the same result, 35. Okay. Let's look at while loop. Again, it's an expression of type unit. So I can do I is equal to reference 0 in while I less than or equal to 5 do printf percentage I slash n I, then I say I is equal to I plus 1, then I call done. It prints 0, 1, 2, 3, 4, 5. Okay. So this is the condition till I value of I less than or equal to 5, and then you print. So for breaking loops, you have to use exceptions. So throwing the exit exception is a recommended way to immediately exit from a loop. So let's try this example here. Try print n line, press escape to exit. Then I say while true do get a character in if c is equal to 0 through 7, this is escape character, then raise exit, whereas I just print character, flush std out, close the while loop, try with exit. Okay, press escape to exit. So I'm going to say A, B, C. If I press escape, it exits, right? So that's the logic here. Now we look finally on the references inside closures. And so here we are creating a function called create counter, which returns a closure that hides a mutable value reference n. Let's define that first. Let create counter, we say let n initial value 0 in, and there is a function here which increments n and returns n. So this reference will hold the state of the counter. Okay, and then we define the closure that takes no arguments, right, which is this one here. Right, the closure will increment the value of n and it will return the current value of n using this one. Right, so let's use this create counter. So I'm going to say let C1 is create counter. I'm going to create another C2 as create counter and ask for C1, returns 1. Again call C1, it will increment 1, so it will return 2. Then I ask for C2, returns 1. And now if I ask for C1, it will increment 2, the previous value, by 1 and it should return 3. Okay, so that state is a sort of maintained inside the closure. So let's stop here, and then the next session we will go through some of the recommendations for handling immutable state inside FX. Let me paste the link to the YouTube channel where this video will be available. I suggest that you try this example on YouTube. After watching YouTube, you try it on UTop and also watching the video again. Let me paste it in the chat. Do you have any questions at this point in time? The notes from the session are also available on this GitHub repo. So with that, let me stop the recording